So let's say you want to build a computer that can play Scrabble. One algorithm for setting that up comes from this research paper called The World's Fastest Scrabble Program from May 1988. Now, they give an algorithm that works to generate, like, the hard part of, well, a hard part of this problem is figuring out which moves you could make. And so they have an algorithm for doing that. And they give you the pseudocode, but they don't really explain why that works. And so if you want to understand why this algorithm works, you're kinda on your own. Until now. Let's build that algorithm from scratch, from the ground up. So, the first thing, I'm going to be working in Python here, because Python makes it easier to see the algorithm, because there's less, like, language-related cruft that we have to put in. Okay, so they mention that they put their dictionary of words that are valid in a letter tree. And so the way the letter tree works is it's a tree, so you've got nodes, and then the edges of the tree get labeled with letters. So if we want to ask the question, is cars in this letter tree, then we start at the root of the tree. We follow the edge labeled C, and then labeled A, and then labeled R, and then labeled S, and this node is marked as, yes, this is a final node, so if your word ends here, then that is a real word. But if we want to ask, is EA a word, then we follow the E, we follow the A. This is not the end of a valid word. And if we want to ask, like, is QFG a valid word, we start at the root, there is no Q, so we fall off the tree. Now, this structure makes it, like, this structure means that if we're building a word from left to right, we can, like, at any given point, we can say, okay, which letters can come next, and this tree structure, like if we are at this node, like if we got E and A, if we want to know which letters could come next, we can just ask the tree, hey, we're at this node, what letters can we use to get from here to another place in the tree? And so if we had EA, we know that, like, Q can't be the next letter because there isn't an edge out here that's labeled Q. And so we want to go ahead and implement this for ourselves. So I've got a word list here with 850 words in what is known as basic English. So we'll make a Python file, and that'll be lettertree.py, and then we will have a node. And we will store the children in a Python dictionary, because the Python dictionary is a good way to, like, if that's lets us map from keys to values, and then the key can be the letter, and the value can be the node that we get to if we take that letter. And so the tree itself the tree has a root node, and the root node is not a word. And so I'm going to go ahead and have also pass in a list of words as a constructor argument for the letter tree. And so for each word in that set of words that's our word list, we want to add that to the tree, and the way we do that is we keep track of where we currently are in the tree. We start at the root, and then for each letter in the word, if that letter isn't if there isn't a node that we would go to, if there isn't already a node that we want to go to next, then we will take the children and say that with the key of that letter, you should have a value of a new letter tree node. And as far as we know, it's not a word, at least so far. And so now, whether it was before or not, now we know that there is a node that we can get to if we say, okay, from the current node, let's take that letter. And so if we move to that node, then we have successfully processed that letter, and by the time we've processed all of the letters, we are at the node for the end of the word. We can say, hey, this node is in fact a word. Now, this would technically be enough, but it'll be helpful to have some helper functions. One of them is lookup, which we can pass in a word and it'll give us the node for that word if it exists. And so that iteration is going to look kind of the same. If the letter is not in current node children keys, then, but we don't want to make a new node here. If we fall off the tree, then we just want to give up. There's not a node here. And so yeah, so lookup, we pass in a word, and it'll either return none if there is no node, or current node if it found a node. And then another function is word. Look for that node. If we didn't find it, if we fell off the tree on the way there, then it's definitely not a word. And if we made it there on the tree, then we want to say, okay, that was a word if the node that we got to is marked as being the end of a word. And so then we'll make a helper function, basic English, that will build a letter tree out of that basic English word list. Open that file, read it as text. Empty list for word in line in file, word line strip, because when we loop through a file like this in Python, it brings in the new line character, and we don't want to have that. And so now we have a list of words. And we can build a letter tree from those words. And so now we have a way to represent our dictionary. And that's already enough to handle the simplest case. The simplest case is nobody has played anything yet. The board is completely empty, and all we have to do is look at all of the words that we can build with the tiles that we have. So I'm going to bring in that helper function, and then to make things, in order to make sure that we're grouping all of our like solving related state together, I'm going to make a class to represent that. And then give it a constructor, it takes in a dictionary and the tiles that it has in the rack. And it just hangs on to those. And then we would like to be able to get all of the words that we can make. So we have this tree structure, and we would like to do, essentially what we're going to wind up doing is, like, essentially it's just a search in the tree. And since we're trying to get all of the options, then it doesn't really matter if we do a breadth-first search or a depth-first search. I think this winds up being depth-first. Yeah, this winds up being a depth-first search, but it doesn't really matter. The important thing is we're going to implement this recursively, because that'll make our code a little shorter. And so all words, if we want to get all of the words that are reachable, we can have a current node, and that'll start out at the root, and then we can do a recursive graph search, or tree search, yeah. It's a subset. But yeah, so if we want to get all of the words that are reachable, well, if we are already at, like, if the place where we got to the place where we are, so it's definitely reachable. If it's a word, then we would like to write that down. And for convenience's sake, like, if you were building a full Scrabble AI, then you'd want to do more, like, you'd want to, like, figure out how many points a move is worth, and, like, use that information to make a decision, but that's not, like, that's outside the scope of the paper that we're looking at, so that's outside the scope of what I'm going to do here. So if we got a legal move, if we have a word that we can play, we can say, okay, we'll print the word that we know how we can build. And so if we made it to a, if the node that we reached is a valid word, then we would like to write down, hey, we got that word. Unfortunately, we don't actually know what the word is that we built yet. We could put that information into the node, but that's kind of inelegant. And a simpler solution is to also have it as an argument. Partial word as an argument, so that then partial word is our argument here. Okay, so now we've looked at the current node. If it's a valid word, we print it out. And so now we want to see where we can get from here. So we will ask the node hey, which letters in the dictionary can I put as the next one? Like, which letters can come next that'll be part of a legal word? And so that'll skip, like, things that the dictionary, so now we only have letters that the dictionary says can come next. And so if we have that letter and we could play it, then we want to say, okay, let's recurse. And let's take the partial word we already had, add in that letter, and take the node that we get when we take that letter in the graph. And then let's add a utility function to start off our recursion. And when we start off, we don't have a word, and the current node is the dictionary root. And so if we want to be able to test, then let's make a solve state and use the basic English dictionary, and our rack will give ourselves the tiles F, L, O, O, and R. And then ask the solver to find all of the options, and we should be able to get floor. So let's run this file, and we can find floor. So that's nice, but there's kind of a problem. One of the words that it found is off, but we only have one F. We can't play a tile more than once. So one way to solve that is say, okay, if we want to play that letter from our rack, then we can remove it from the rack and then recurse with it in the partial word. And then put it back into the rack once we're done. So essentially, the next letter, we take it out of the rack and put it into partial word. And then when the recursive call returns and it's back out of partial word, then we put it back into the rack. So any given letter is either in the rack or in the word that we're trying to play at any given time. So we should only ever have one copy of F. And if we run our program again, you can see that we do in fact no longer build off or roll. So if all we have to do is get a list of words that we can build from scratch, then this code will actually be enough on its own. But that only works when the board is empty and we're just picking a word to put down. Most of the time the board is not empty, and we need to play based on what's actually on the board. So we need a representation of the board. And so when you create a board, you pass in a size, and it remembers size, and it's going to keep track of a tiles. And we're going to make that a private variable so that it's only accessible from within the board. Python doesn't actually have private, but the closest we've got is if we say that if we put an underscore at the beginning of the thing, then that means that we're pretending that it's private, and then if we try and use it somewhere else, it'll work, but my IDE PyCharm will yell at me if I try to do that. That makes sure that the board presents a consistent abstraction, and we don't want to the board is responsible for keeping track of where the tiles are and how it stores the tiles, and then we use the board in the ways that it tells us it can be used. So we'll build up a bunch of, so different size times, we will make a new row. Size times, we will add to that row none. We will use none, which is the Python's null, to indicate there isn't a tile on that square. And then once we've added that many things to the row, appends that to the tiles. Now, if you work with Python, you probably know that there are more concise ways we could build that, but I don't want to make this only make sense to people who know Python. So we will give our board a toString, and I know I just said that I wanted this to make sense to people who aren't Python professionals, but I'm going to do this concisely because I did it like that in my notes, and I don't feel like redoing it. And also, the way that this toString works doesn't really, like, that's out of scope for, like, the actual paper. This is just a debugging tool. The important thing is that it takes tiles as they exist, but if they're none, it uses an underscore. It puts them together in a row, and then it puts the rows together with new lines. And so the board, so this, in theory, would be enough for the board to represent a Scrabble board, but we also want to make sure that we're going to be able to use this in all of the ways that we need. And I did this video once already, so I know which things we're going to need. And one of the things that we're going to need is a list of all of the valid positions in the board. And so that's going to be an empty list, and then row and so we will use a pair, a row comma column. And so that's a Python thing where we can take that pair, and that's a single value that we can put into the result. So now result is a list of all of the valid positions in the board. And we are using row and then column. We are not using X and then Y. A lot of times, like anytime you've got a 2D array, the potential is there to get mixed up and confuse yourself and put the wrong thing in the wrong spot. So what I always do is I decide at the beginning, am I doing X, Y, or am I doing row column? And I pick that, and I never change it. Since the row is a Y and the column is an X, then if you get mixed up, then you're going to wind up with everything working in not the way that you wanted. So we are using row column. We are not going to do X, Y. If we see an X or a Y anywhere, it means that I forgot. And so this gives us a list of all of the positions. And so if we have a position, we would like to be able to get the tile at that position. And so we can break that pair apart. Python lets us do that with row, comma, column equals position. And so we can get the tile. It would be nice if we could also set the tile. Position. And argument for what we're actually setting it to. Tiles row at column is equal to the thing we're trying to set it to. And then another thing that's going to be helpful is a way to check if a position is in bounds for the board. And so row is at least 0, and row is less than self.size, and column is at least 0, and column is less than self.size. And these comparisons are the way that they are because Python has zero-based arrays. So the first index into an array with length size is 0, and the last index is self.size minus 1. So 0 is a valid index, but self.size is not. And this is trying to tell me to do fancy Python things, but I don't want to do fancy Python things. Don't at me. Okay, so we can get a tile based on a position. We can set a tile at a position. We can ask if a position is in bounds, and we would like to also be able to ask, is the square at this position empty? And so we say, okay, first we check if it's in bounds. If it's not in bounds, then it doesn't, like, we don't want to try and look for a tile that doesn't exist. If it's not in bounds, then we say, nah, it doesn't count. So we get the tile is none, as we use none to represent an empty tile. But we would also like to be able to ask about squares that are filled. And a square is filled if getting the tile is not none. So essentially there are 3 options for any given position. It's out of bounds, it's empty, or it's filled. And then one last thing we're going to ask the board to be able to do is make a copy of itself. And so we make a new board. We go through all of the positions in this board. We set the tile at that position to get the tile at that position from ourselves. Okay, and this will come in handy because if we want to say, okay, what would the board look like if we play this, then copy and set tile will let us do that. Okay, so those are all of the methods that we're going to wind up wanting for the board. And then, just like we did with our letter tree, let's make some sample data. Let's make a 7x7 board. Let's set row 1, column 1 to O, and row 2, column 1 to F. And then let's go back in over here. Import that sample board. When we make the solve state, take in a board. And then pass it the sample board when we create it. Print out that board. Print a new line. Okay, so we can see that our board that we built is empty, but there's an O and there's an F over here. And so we are finding, we're finding all of the same things because we haven't changed the logic for finding things, but what we would like to do is be able to play we would like to be able to build FLOOR. We would like to be able to build the word floor here. But since the F is already on the board, we would like to be able to build it with just LOOR in our rack. And currently, we can't do that. So now we have to actually look at the things that are in the board and figure out where we can play things. So one thing we're going to do, because there's a lot of variables and stuff that we have to consider, and any excuse to simplify this is going to come in handy. So we're going to assume for now, like, essentially there are two kinds of moves. Ones where all of the tiles we play are in the same row, and ones where all of the tiles we play are in the same column. Now, the logic winds up being kind of symmetrical, so if we're careful with how we build things, we can build it pretending that everything is across, and then go back in later and also let things be down. So we have across moves where everything's in the same row, down moves where everything's in the same column, and we are going to pretend that across moves are the only ones that matter for now, and we will come back and revisit that decision at the end. So we're going to go ahead and make ourselves some helper functions that let us move around on the board. So if we have a position, we'd like to be able to go left from that position. We can split a row and split it up into row and column. Column -1, put it back together. And so that'll let us go left. To go right, we go to column +1 instead. To go up, we return row -1, and the column stays the same. And for down, we add 1 to the row, and the column doesn't move. Now these, we could put this logic everywhere, like the logic of split it apart and then put it back together, but slightly different. We could put that all of the places where we make moves, but having it all live here means that it's easier to read our code that's coming later on, and it means that when we come back later and handle down moves instead of just across moves, these, if we're clever, these are the only places we'll have to change. Okay, so we have that conveniently available for us. So when we play a new word, it has to attach to the existing tiles somewhere, if it's not the first move. So somewhere our word has to attach to a tile that already exists. So at least one of the squares that our word goes on is going to be empty, but next to something that is filled. So like for floor that we want to build, the L that goes here is attached to the F. And so we're going to say that a square on the board that is empty but next to something that's filled, that is an anchor square. And so we're going to add a method to our solve state that can find a list of all of the anchors. And so we can look at all of the positions. So an anchor is defined by being empty and having a neighbor that's filled. Going left gets us to something that's filled, or going right gets us to something that's filled, or going up gets us to something that's filled, or going down gets us something that's filled. So we look left, look right, look up, look down, and is filled does the bounds checking for us, and left, right, up, down handle incrementing whichever piece is the one that needs to be changed. So like this code, even if we weren't planning ahead for changing what directions, like how directions work, then these helper methods would still be useful to have. because that makes this code way more readable. So we know if we're empty, we know if our neighbor is filled, we have a neighbor that's filled. If we are empty and we have a neighbor that's filled, adds the position to the list of anchors. And then we can just return that list. So that lets us calculate all of the anchors. And so just to test that that's working correctly, ask, okay, so find the anchors, give us that list for every position in that list. Let's put something in the board that'll let us make sure that our anchor's in the correct spot. And then, because I'm a tryhard, let's put an anchor emoji in all of the spots that it finds that are anchors. Okay, so it's telling us that these are anchors, and those are the places that are empty, but next to squares that are filled. And so that works. So a word that is attached to the words that are already on the board is a word with a tile that's on one of those anchor squares. So if we want to build only the words that we can actually play, then we can start from those anchor squares. So the easy case is because we're trying to build floor, and so the anchor that we want to use when we build floor, if we look to the left, there's an F that's already there, which means that we are continuing based on, we know exactly what comes at the start, because we know that it's an F, and we just have to follow that F. And so, we have our all words. If our partial word is F, and our current node matches with that F, then that'll let us fill in the L, the O, the O, the R, and build the word floor. So we would like to be able to do that. So in our find all options, this is going to have to get more complicated. So we're going to have to get all of the anchors, because the anchors are the places where we can start building words. Then go through each of those anchors. And then at that anchor, we look to the left and see if there's already something there. And if there is, then we know that we are continuing off of a something that already exists. And we want to... So we say, okay, so we want to get the entire thing that already exists. If we had IF or some other word, if F was just the last letter in a word, then we would want that entire word, because we have to build off of that entire word. So we need to grab the entire set of tiles that's to the left of this anchor. And so we're going to scan to the left. So we're going to have a position where we're scanning, and that starts to the left of the anchor. And then the partial word, as far as we know so far, is get tile at that position, because isFilled did bounds checking, and we know that scan pause is on the board, and there is a tile there already. So partial word, we can grab that tile, and then while we can still go further left and there's more tiles, we want to go ahead and go further left. And add whatever we found at the beginning of partial word. Okay, and so now we have run out of letters, scanning to the left. And so now we have the partial word that's all of the things that we're building on. And so all words takes the partial word and the node. And so we'll have the partial word node. Ask the dictionary to look up the partial word. And then if it didn't find a node there, then we can't make anything by building on partial word node. The dictionary is just like, no, give up now. And so we will, in fact, give up now. But if there is a node there in the dictionary, that means we could build... There are words that could be built that start with that, and so we would like to go ahead and find them. Okay, so if we run this, it says that it can, in fact, find floor. Let's make sure that it's putting floor in the right spot. So let's go ahead and say, okay, what would the board look like if we printed that, if we played that? Make a copy of the board. And then, okay, so we also need to, because we need to know where the, where this word is getting played. And since we're building the word from left to right, then when we find a word, the position that we found it from is going to be at the end of the word. And so the position... And so the position that's convenient to get to from where we are at in legal move is the position of the last letter in word. And so we're going to essentially backtrack through the word and play one letter at a time. And then, while we still have a word left to play, check the board if we played that. Set the tile at that position to the word letter that we're looking at. Subtract 1 from where we are in the word. Move left on the board. Print the board if we played that word, and then a new line. And so now, all words, we call legal move in all words, we need to tell it the position that we're in, but we don't know the position that we're in yet. So what we're going to do, the way that we know what position we're in, only works if, only works when we're building to the right of the anchor. So what we're going to do is take all words, make a copy of it. We're going to comment out the original. It's a surprise tool that will help us later. And then, so this method, we're going to say that this is, because we're taking a word and we're extending it to the right, and so we will call this method extend right. And so we will also keep track of a position. And the position, because, the first thing, because the way that extend right works is first it plays, the partial word if it can legally do so. And then it puts down a letter at the position that it's currently looking at, which means that the position that it's currently looking at is actually the position of the next letter, and the position of the last letter in partial word is one left from next position. And now that we have the position of the next letter, we can actually also make sure that we don't run off the edge of the board if the position of the next letter that we're trying to play is in bounds. Then we go ahead and do this recursion, extend right, and also move next pause one to the right. And so yeah, we check this. Yeah, so we check this after, because if the next if the next letter that we want to print, if the next letter that we would be playing would fall off the edge of the board, but we haven't played it yet, then we totally could still have a legal move that's worth playing. Because since next pause is after the end of partial word, then playing partial word we can do before we check to see if next pause is in bounds. And so now this is extend right, and it takes another argument, and that's going to start at the anchor position, because it's trying to fill in the anchor, and then stuff after the anchor. And so now if we run, then found a word floor, and it puts floor there. Found a word or, it puts or there. And also found 4. Okay, so we have, when we have the F already on the board and we have LOOR available, we can use the LOOR along with that F to build floor. But what happens if the R is also already on the board? Set tile row 2, column 5 to R, and take that away from the rack. And it no longer can find anything. Because when we're extending a word to the right, if we see a tile that already, if we already if there's a letter that's already down there, then we don't need to worry about playing something, because we can just include what already existed. So if the next position is in bounds, then if it's empty, then we have to pick something to play in it. But otherwise, we can say, okay, there's already something here, so we can grab the existing letter, and then if it would be if taking that letter, if the dictionary says that it's okay to take that letter, then we want to go ahead and incorporate that and recurse. Okay, so yeah, if the place we're trying to put if the next place we want to try and put a tile is empty, then we put a tile there. Otherwise, we check to see what tile is already there, and if the dictionary says, yeah, go ahead and use that, then we go ahead and use that. So now we can find floor again, and that's nice. But that's actually too permissive, because now if we try and put LAL in the rack, then we can find, then it says, oh, we found a word fall, but the word that we've actually built is fall R. And that's because if the current node is a word, but there's a letter coming up after it, then it doesn't matter if partial word is a word, if there's an unpleasant surprise coming up that means we haven't actually built a word. So one way to do that would be to make sure that the next position is empty before we try and say, before we celebrate that we've got a legal move, we say, okay, we have to make sure that the board is empty at that spot, because if there's a letter coming up, then we don't want to celebrate yet, because we don't actually have a legal move. And so we no longer find fall. But if we put UTUE, then we should be able to find future. FUTURE. But we don't find future. And the reason that we don't find future is empty. The way that we built that is if the position is out of bounds, then is empty will return false. And so what we want to check, is empty isn't actually enough. We want to make sure that there's not a next letter coming up to surprise us out of nowhere. So instead of is empty, we can use not is filled, because the options are filled, empty, or out of bounds. And we want to include empty and out of bounds, so we can say not filled, and that will give us, that'll let it find future. And if we put this back to LAL, we still don't find fall R. And if we put this back to OO, we still find floor. So this works for what it is. But let's take the R back out, and let's say that we have EFFECT in our tray. We should be able to build effect down here, anchoring off of OF, because the first F in effect will land here, and that builds off. And so that's attached, and that's a perfectly legitimate word. So find all options only covers the case where we already have stuff to the left of the anchor. If we don't already have anything to the left of the anchor, then we have to decide what to put there. We need a left part before the anchor. And so we can go back to all words, the surprise tool that was going to help us later, and we can call this left part. And so left, when we're filling in the part before the anchor, because this function is now working to answer the question, what can we put before the anchor? And so whatever we got to, whatever we have already is a thing that we could put before the anchor. So let's fill in the anchor and everything after the anchor. And, okay, so that needs an anchor position. Let's pass it in as a parameter to left part. And then we look at the next letter. We start building words. Start building a left part, and the anchor position still stays the same because we're trying to fill in to the left of the anchor. And so whatever we come up with to put to the left of the anchor isn't moving. And so if the board to the left of the anchor is not filled, then we can generate a left part, and partial word can start out with nothing. We start at the root of the dictionary, and it's the anchor position. So if we run this, we find effect in the spot where we wanted to put it, but we also find it in a lot of other spots, like here, like it's wrapping around the board. We don't want it to do that. The reason that it's wrapping around is Python arrays are like that. Uh, we're falling off the edge of the board, and we would like to not do that. And so we need to only use as much space as we actually have, so we need to figure out what the limit is on the length of the left part. And so we will once again be scanning to the left, but instead of looking for filled squares, we're looking for empty ones. Or we're looking for ones that are in bounds. Empty is going to come up later. Empty is going to come up now. And empty only returns true if it's also in bounds, so we can use that. And so yeah, if the place that we are thinking about putting our left position into, if that is empty, then we add one to the limit. And we move scan position further to the left. And then that limit is the longest left part that we can have. And so if there's more room left to add another letter to the left part, then we will do all of that work. And we've used up a character worth of our room to add left part. So now we aren't wrapping around the edge of the board, but we are building oaf across, and we're building foff across, and we're building eof across, and none of those are words. So we need to make sure that none of the words... So we need to make sure that we don't accidentally build any words going up and down that aren't legal. So we want to, like, when we're about to put down a tile, we want to make sure that putting that tile there won't create an illegal word. So we want to check where, like, we want to check based on the words that go across. Like, okay, because we're already going across, so we want to check the words that go up and down. And make sure that we don't build any invalid words. And so we could, like every time we're about to put down a new tile, check, okay, if we put this tile here, are we going to build an invalid word? But a different approach is to just like run that check ahead of time and reuse the results. So if we want to check like run that check for every square on the board, then we can reuse those results later on. So we want to take each position on the board and figure out which letters could legally go in that position based on the tiles that go up and down. So we'll use a dictionary, and the keys are going to be positions, and the values are going to be lists. For every position that's in the board. If there's already something here, then we don't care. We don't have to look at it, because there's no way we can put a tile there because there's already a tile there. So we're going to look at the letters that go up from this spot. And we're going to do a similar scan to what we do down in Find All Options. We're scanning upwards. And we take the new letter and add it at the beginning of the letters that we already had found. And then we do the same thing going down. But instead of at the beginning, new letters that we find come at the end. And so, now we've looked up and we've looked down and we've found all of the letters that are right next to this square. And so if there aren't any, up and there aren't any down, then this isn't next to anything, and we know that it could be, like, all of the letters are legal here. So we're going to take this string and turn it into a list of letters, and then legal here is a list of all of the letters that exist. Otherwise, we know that there are some letters that could cause some issues. So legal here, we start out with nothing. For all of the letters, we say, okay, what word would we form if we put that letter here? If that is a word, then that letter would be legal to put here. And so now we've got a list of letters that are legal to put here. Now, in theory, we could save some time by doing a dictionary lookup on letters up ahead of time, but I'm lazy and I don't want to do that, so we're not going to do that. Because we have an is word already, and we would have to re-roll that if we want to is word starting from someplace other than the root. So we're not going to do that, we're just going to use is word. Because we don't want to allow part of a word, because it's not legal to build part of a word going across. It has to be all of a word, or just a single letter. So yeah, we build the cross-check, and so the cross-check for a position can tell us which letters are legal to put in that position. And so extend right when we are about to put down. Okay, so we would like to only run that once and reuse the results every time, like reuse the results. So we'll start that out as none when we construct the thing, and then in Find All Options, we'll calculate and put that in self.crosscheck results, and then when we are about to put down a new letter in extend right, we will make sure that that next letter is in the list of letters that would be legal to put at that position. So now extend right, when it puts down a new letter, makes sure that it won't build any illegal words. Now, for left part, that's a little more difficult because where a letter goes in left part depends on how many more letters we put after it, and we don't know how many more letters we're going to put after it because it could be any number of them. So it would be nice if we could just not have to deal with that. So, like, the left part, if we can just stop that from having to deal with that, then that would be cool. So, like, if we want left part to avoid the places where the cross-check can matter, then it's actually totally possible to do that, because the places where the cross-check matters, like, the cross-check only matters if if there's a tile above or below that position. And if we want left part to ignore tiles that are empty but have neighbors that are full, then we have a term for tiles that are empty but have neighbors that are full, and those are the anchors. So, since we always extend right from an anchor, then telling extend left to stop if it sees an anchor means that we don't have to, like, we aren't going to miss anything if we do that. Because extend right will always start at an anchor, go to the right. So left part can, so like left part, if it would hit an anchor, it can just like stop before that. So we can take this while loop and say while the left is, while the board says that it's empty and that position is not one of the anchors. Because if it is an anchor, then either then there could be something above or below it, and we definitely already ran extend right from that, so we don't need to recheck any of this. Like, we already have anything that covers that anchor, and so we don't need to go back over it again from the left. So we can skip anything that's an anchor. And so that should prevent us from finding effect crossing with EOF or effect crossing with FOF. Oh, is filled. Oh. Just a spot. Okay, so we no longer find effect in places where it forms an illegal word crossing, and if we put the R back in, then we can no longer build effect because RT is not a word. So let's dust off that PDF and look at that algorithm again and see if we can make a little more sense of it. So PDF over here. Resize this to make it a little easier to see the code. So the algorithm that they give, so they have a function called left part. We have a function called left part. Starts by calling extend right. If the limit is greater than 0, then for the things that we can do, like for the children of that node, we take the letter and see if it's in the rack. If it's in the rack, then we remove it from the rack. We take the node that we get by taking that letter, and we do a recursive call by taking the partial word and adding the next letter, using the node that we got from children, and subtracting 1 from the limit, and then we put the tile back into the rack. So we just built the left part that they have here, but we actually understand why this works the way that it does, assuming that I did this right. And you actually understood what I was doing. So they have an extend right, we have an extend right. So okay, so ours looks very slightly different to theirs, because they pull some shenanigans. They say, the way that they handle falling off the edge of the board is, oh, let's just put fake squares with empty cross-check sets. at the end of the row. We don't do that. We just check here. We make sure that it's like we handle bounds checking separately. But for if it's vacant or empty or out of bounds, then if it's a legal, like if it's an entire word, then write that down. And then if it's empty, then we look at the letters that we could take next. We check to see if they are in our rack and in the cross-check results for the square we're trying to put it in. Then we take it out of the rack, follow the child, move to the right, and do the recursive call, and then put it back into the rack. Otherwise, if it wasn't empty, then get the letter that's already in there. If it's a valid thing to do from current node in the dictionary, then move to the right, take that word, and move to that node, do the recursive call. So our left part and our extend right are equivalent to their left part and their extend right. So we just built their algorithm with actually explaining what we're doing in the process. So they do say it is easily seen that the algorithm generates each across move exactly once. I don't know about easily, guys, but if you say so. So there are a couple extra details that they mention. One of them is blank tiles. They actually give a pretty good process for handling blank tiles. Add a little extra code. When we're looking for a letter in the rack, also look for a blank, and if we found the blank, then pretend it's the letter. For now, that's a good description of what you've got to do. I'm not gonna go into that. But what I am going to go into is, remember how we started by saying, there's no such thing as up and down moves? Well, there's such a thing as up and down moves. So what we're going to do is, because the way that we set this up, the only, because essentially whether a move is across or down depends on whether it's rows or columns that the change with each tile in the move. And the only thing that knows the difference between rows and columns in our solver here are these left, right, up, and down functions. So what we can do is say, okay, well, if we can be making moves that go down instead of across, then it's not really left, it's before, in the primary direction that we're moving. And so the function is called before, and instead of left part, we can call it before part, since it's what comes before the anchor. And then it's not right, it's after. And then the method is right, and then extend after, because we're extending after the anchor. It could be to the right, or it could not. And then up is before, but in the other direction. And we don't want to change dictionary lookup. And then down is after in the other direction. And then we'll go into cross-check and say that whenever we have letters before cross, let's rename that variable to just letters before, letters after cross, let's rename that to just after, because this is the cross-check. We already know that we're looking across. Okay, so now these methods, the names are generic over which direction we're actually moving. So let's make the behavior also that. So we'll keep track of a direction in the solve state. we'll say that it starts out as none, and then find all options in across down. And then we do all of that once with in across mode and again in down mode. And then to go before, if we are in cross mode, then before means the same row, the previous column. Otherwise, we're in down mode, so before means the previous column and the previous row and the same column. And then we can't. Can I copy? Okay, it just doesn't want to. Okay, so say after when we're going across is the same row, next column. After while we're going down is the next row, same column. Row plus one column. Before when we're going across is the previous row, same column. Before when we're going down is same row, previous column. After when we're going cross when we're going across is next row, same column. When we're going down, it is same row, next column. And so now if we run, we've built to and to like we used to be, but also we build free and tree and off that go up and down. So we do also find of again, but there are a couple ways we could check for that. One of them is an extend after to keep track of have we filled the anchor yet. And it's only a legal move if we filled the anchor yet. And if we're recursing an extend after, then we know we filled the anchor, because the first move that extend after makes is to fill the anchor. And so if it's making a second move, then we know it's filled the anchor. But if we're making the first move, then we haven't filled the anchor yet. And so now we no longer pretend to have found... We found of, but going the other direction, because we can put an F there. But we can no longer build the of that already existed. We can no longer claim credit for it. So yeah, that is the world's fastest Scrabble algorithm, at least from 1988, built from the ground up and explained along the way. Hopefully that made sense. If it didn't, leave a comment, and I'll try and explain it. And have a nice day.